Welcome to Lecture 17, Shear and Bending Moment Diagrams. In this lecture, we'll be discussing shear and bending moment diagrams, and we'll also look at the relation between distributed load and shear and the relation between shear and moment. We'll be creating shear and bending moment diagrams for beams. A beam is a common type of structural member used in engineering that is designed to support loads applied at various points along its length. Beam design consists of two parts, the first being determining the shearing forces and bending moments produced by the loads and how they vary along the length of the beam. And the second part of beam design is to select a beam cross-section that is best suited to resist the shearing forces and bending moments that have been determined to be present in the beam. In statics, we're concerned with the first part of beam design. The second part will be addressed in your mechanics of materials course. Determining the variation of shear, which we established in the previous lecture, will denote by capital V, and bending moment, which we're denoting by capital M, along the length of the beam of a beam can be accomplished by using the method discussed in the previous lecture. In the previous lecture, we discussed how to determine the internal forces in a member. And the goal is to express V and M as functions of the length X of the beam. Shear and bending moment functions will be discontinuous for values of X where a concentrated force is applied, a moment is applied, or where a distributed load changes value. So we will need to determine these functions for each segment of the beam located between any two discontinuities of loading. Here's the procedure we'll be using to create shear and bending moment diagrams. The first step will be to determine all of the reactive forces, that is the support reactions and couple moments acting on the beam. We then need to express all forces in their component form with those components acting parallel and perpendicular to the axis of the beam. For the second step, we'll work from the left end of the beam, where we'll set X equal to 0, and we'll identify any values of X where the shear and or bending moment functions are discontinuous. Now remember, on the previous slide we identified these discontinuities as where a distributed load changes value, or where a concentrated force is applied, or where a moment is applied. For the third step, we'll cut the beam at the lowest value of X and draw the free body diagram of the beam segment on the left side of the cut. For the internal loading at the cut, we'll use the sign convention for shear and bending moment that we established in the previous lecture. And that is, we'll show the shear force, the unknown shear force, acting downward at the cut, and we'll label that V, and we will show the unknown bending moment at the cut acting in a counterclockwise fashion and label that M. For the fourth step, we'll solve for the magnitude of V and M as functions of X using the equations of equilibrium available to us. And then we will plot those functions, namely the shear function will be plotted in the shear diagram, where we'll be plotting V versus X, and the bending moment function will be plotted in a separate moment diagram, where we'll be plotting M versus X. The fifth step is to now repeat steps 3 and 4 for the remaining values of x where discontinuities exist until the shear and bending moment diagrams for the entire beam have been created. So at this step, we would go back, look at the next value of x where a discontinuity has been identified, and repeat steps 3 and 4, and so on until we have no more discontinuities identified by specific values of x. Let's use the procedure from the previous slide to work through an example. So here we have a beam that's 4 meters long, that's supported at each end and has a 5 kilonewton force applied to its center. So our first step is to determine all of the reactive forces and couple moments acting on the beam. We don't have any couple moments. We do have support reactions, which we can determine by drawing a free body diagram of the beam and solving for those support reactions as we've done in the course over the past few weeks. And we find that those support reactions are both equal to 2.5 kilonewtons, as we suspected based on the symmetry present in the problem. The second step is to work from the left end of the beam, where we'll set x equal to 0, and we'll work towards the right and look for values of x where discontinuities in the shear function or the bending moment function will occur. And as we established a couple slides ago, these discontinuities will occur where a distributed load changes value, a concentrated force is applied, or a moment is applied. So as we work our way towards the right, we come to this concentrated force, the 5 kilonewtons, and a discontinuity will occur there at x equals 2. So we note that, and we continue on after the 5 kilonewton force. And the next discontinuity will be experienced at x equals 4, where the 2.5 kilonewton support reaction is. Okay, so we have two values of x where discontinuities occur, which means we're going to cut the beam twice, and for each cut we're going to solve for V and M and express V and M as functions of x. So let's look at the first cut we're going to take. So this is step 3. We're going to cut the beam in this first section here between 0 and 2. Draw the free body diagram of that, which I've shown uncovered here on the upper right hand of the slide. And that free body, on that free body diagram, we need to make sure that we show the unknown shear force acting down at the cut and the unknown bending moment acting counterclockwise at the cut. And this is the convention we established in the previous lecture, and how we're going to do all of these shear and bending moment diagrams. We're always going to show the shear. We're always going to work from the left. And when we cut the beam, we're going to show the shear acting downward at the cut and the bending moment, the unknown shear acting downward and the unknown bending moment acting counterclockwise. Now, the important thing to note here is that the functions that we produce here for V and M are good for the entire segment of the beam between 0 and 2. So we took the cut at some arbitrary distance x from the end of the beam. Okay, so let's hold on to that for a second and let's solve for V by summing forces in the y direction. And we find that V equals 2.5 kilonewtons. And we'll solve for the unknown bending moment by summing moments at the cut, setting those equal to 0, setting that summation equal to 0. And when we solve for M, we see that M equals 2.5x kilonewton meters. So the moment of that 2.5 kilonewton force about the cut is 2.5 times the distance of that force from the cut, which is x. And you usually label your free body diagram with the region of the beam, the segment of the beam that the free body, that the functions V and M are good for. So these two functions, V and M, are the functions of V and M when x is greater than or equal to 0 or less than 2 meters. Now, along with solving for those, which is step 4, we're going to plot those. And we generally show the plots right underneath the free body diagram of the entire beam or the figure of the entire beam. So in other words, we're going to have our x-axis, start at 0 and end at 4, right underneath the free body diagram of the beam, so it's easier to visualize what's going on in the beam by having these diagrams directly under the beam. So now we go back to algebra here, and we plot our shear function for this section of the beam, this segment of the beam, and we saw that V equals 2.5 kilonewtons, so we plot that. Okay, where here's x equals 2, and we establish some scale on our vertical axis here. So this would be V equals 2.5. And the standard practice is to shade in the area under the function, or I should say the area between the function and the horizontal axis. Okay, so that's V equals 2.5. V is just constant, is not varying with X. And then M is 2.5X. So when X equals 0, M equals 0 down here. And when X equals 2, M equals 5. So we'd plot that there. And then we would have on our scale out here on the vertical axis, say 5. Okay, so that's step 4. Now step 5 was to repeat 3 and 4 for the remaining values of X, or the remaining segments of the beam that we've identified. Okay, so we have to now take a cut in this portion of the beam between X equals 2 and X equals 4. Draw a free body diagram of that, of the segment of the beam to the left of the cut, and notice that we draw the free body diagram of the entire segment of the beam to the left of the cut, not just back to the previous cut, but all the way back to A. Okay, and we use our free body diagram skills to complete that free body diagram, showing the 2.5 kilonewton force that's there, showing the 5 kilonewton force that's applied to the beam. At the cut, we're always going to show V going downward, M going counterclockwise. And then notice here, the distance from X equals 0 to the cut is always going to be X, which means that this distance here is going to be X minus the 2 meters. That is the distance from the start of the end of the beam to the 5 kilonewton force. Okay, so you need to look at this free body diagram closely and make sure you understand what's going on here with the distances. X is always going to be the distance from the left end of the beam to the cut. Okay, so now we'll sum forces in the y direction, and now we find that V is negative 2.5 kilonewtons because we had 2.5 kilonewtons at A acting upward, 5 kilonewtons at B acting downward. So V must be acting upwards at 2.5 kilonewtons, opposite the direction we assumed. So it's a negative 2.5 kilonewtons. And now the sum of the moments at the cut, pay attention here. We set those equal to 0. And we have the moment of the 2.5 kilonewton force at A about the cut, which is a negative 2.5x. We're assuming that positive moments act counterclockwise. And now the moment of the 5 kilonewton force about the cut is 5 times its distance from the cut, which is x minus 2. There's that x minus 2. And then, of course, plus the unknown moment at the cut, which we've drawn in a counterclockwise manner. So we do that algebra, and we get that m equals 10 minus 2.5x kilonewton meters. So now we plot that, go back to our algebra skills, and when well, let's look at it. Let's look at the shear and the moment function plotted. So first we're going to plot the shear. V equals negative 2.5 kilonewtons. So that's going to be shown here. And we'll fill in that area between that shear curve and the x-axis. And when we plot the moment function here, we get a line, it's linear, that starts at m equals 5, and at 4 it goes back to 0. And again, it's already shaded here, but when you do these, you would shade in the area between the curve and the x-axis. That took a little while, but this is the gist of shear and bending moment diagrams. Now let's consider the relation between distributed load and shear. To do so, we're going to consider the free body diagram for a small segment of this generally loaded beam, and with the free body diagram shown here. And we're not going to go through the derivation, but by summing forces in the free body diagram that are in the vertical direction and setting them equal to 0, we can show that the slope of the shear function or the shear diagram is equal to the intensity of the distributed load, and that the change in shear in the shear function between two values of x is equal to the area under the distributed load loading curve between those two values of x. Let's see if we can apply those relations between shear and distributed load to the example problem we did. So we said on the previous slide that the slope of the shear curve is equal to the intensity of the distributed load. So we look at our shear curve, and it's just a horizontal line for this segment of the beam, and the slope of a horizontal line is 0, which means that the intensity of our distributed load must be 0, and that checks because we had no distributed load, or we had a distributed load with an intensity of 0. So that checks, and we can check it for the second part of the shear curve for this segment of the beam. Another horizontal line, slope is 0, so therefore the intensity of the distributed load for that section of the curve, for that section of the beam, segment of the beam, is also 0, which checks because we had no distributed load to begin with. The second relation we established was that the change in shear between two values of x is equal to the area under the distributed load curve. And again, we had no distributed load, so we would be expecting no change in shear for each segment of the beam. And we go back and look at our shear curve. And again, for a horizontal line, there's no change in shear between any two values of x. So this one checks also. Delta V for all values of x is, between any two values of x is 0, which means there's no area under the load curve, loading curve, which means there's no loading curve. So how do we use this? Well, there's two ways to use these relations. The first is, after you've done a problem like this example problem, you can use this as a check to make sure, as a sort of a sanity check, to make sure that you've done the problem correctly and drawn the curves correctly. The other way to use these relations is, once you get better at drawing shear and bending moment diagrams, you can actually use these relations to help you construct the shear diagram. We're going to do the moment relations in a second here, but it can help you construct the shear diagram, especially when you have lots of things going on the beam, where you have distributed loads, you have concentrated loads, and so on. So you can imagine if you have multiple concentrated loads and moments applied and distributed loads that are changing, you can end up with multiple segments of beam to analyze, and that can get very tedious. And again, once you get more used to shear and bending moment diagrams, you can use these two relations to help you sort of take some shortcuts and draw the shear diagram without having to go through that procedure that we went through for every single segment of the beam. But for now, we'll just use it to check our work after we've used the procedure that we established. And now let's look at the relation between shear and moment. Again, we're going to consider the free body diagram for a small segment of a generally loaded beam. Here's the free body diagram, the same free body diagram that we used a couple slides ago for the relation between shear and distributed load. And now, instead of summing forces in the vertical direction, we're going to sum moments and setting them equal to 0, because that segment of beam is in equilibrium. It's not moving anywhere. And when we do this, again, we're not going to show this derivation, but we can show that the slope of the moment diagram is equal to the shear at any point x. and that the change in moment between two values of x is equal to the area under the shear curve between those two values of x. Now let's see if we can apply the relation between shear and moment to our example problem. So we said on the previous slide that the slope of the moment curve is equal to the shear at any point x. So we look at our moment curve here for the first segment of the beam, and it has a slope of 2.5, and it's a constant slope, it's a straight line. And we look up at our shear curve, and shear is a constant 2.5. So that checks. Now let's look at the second portion of the moment diagram, where the moment is equal to 10 minus 2.5x. So the slope here is negative 2.5, and it's a straight line, constant slope, and our shear for that entire segment of the beam between x equal 2 and x equal 4 is a constant negative 2.5. So that checks. Now the second part of that relation was that the change in moment between any two values of x is equal to the area under the shear curve between those two values of x. So let's look at, again, our first segment, where we'll take our values of x as 0 and 2. The change in the moment between x equals 0 and x equals 2 is the moment starts at 0, and at x equals 2 the moment is 5 kilonewton meters. And the area under the shear curve between 0 and 2, it's just a rectangle, so it's just going to be the 2.5 times 2. And remember, this is 2.5 kilonewtons times 2 meters. So the area under the shear curve is 2.5 times 2, or 5 kilonewton meters. So that checks. And then for the second segment of the beam between x equals 2 and x equals 4, we see that if we look at delta M between 2 and 4, M is changing from 5 to 0, so it has a change of negative 5, and the area under the curve, or the area between the shear curve and the x-axis between 2 and 4, is this area here, and we would consider that area as negative area because it's below the x-axis. So it's negative 2.5 which is this side of the rectangle, times 2, or -5. And again, the units on those are kilonewton meters for both of them. So that checks. So again, this relation between shear and moment, we can use that to check our work, or as we get better at these shear and bending moment diagrams for more complex ones, we can use that relation to help us actually create the diagrams without having to go through multiple free body diagrams for multiple segments.